In this video, we'll look at two improvements to trees called bagging and random forests. So first off, why would we even want to consider improvements to trees? Aren't trees awesome? Well, they are. They're very interpretable. But it turns out that decision trees by themselves aren't super accurate. Well, not to fear, it turns out that there are tweaks that we can make to trees that aren't too zany or weird that can make them very powerful in terms of predictive ability. We'll look at two of these ideas in this video. The first idea is the idea of making many trees. So I said that a single decision tree is not that accurate by itself, but can we make many trees? So growing a large tree is nice in that it gives us a sufficiently complex model, but we know that complex models suffer from high variance, right? This is the bias variance trade-off in play. When we have complex models, they have low bias, but complex models we also expect to change a lot when we have slightly different training data. They have high variance. Okay, well, can we somehow keep that large, low bias tree, but somehow reduce its very high variance? That would be the ideal. It turns out we can, but how? The idea will be to take predictions from lots of trees and average them together. This is the idea that averages of measurements are less variable than the individual measurements themselves. So this is an idea that probably came up in Math 155 when you learned about the central limit theorem. So what I'm showing in this picture is the black distribution is the distribution of values for a single measurement. So this distribution shows different possible values for a single measurement from -3 to 3 approximately, and the relative probabilities of the measurement taking those values. What we see is that the black distribution is pretty spread out. It's very wide. So in a sense, single measurements are fairly variable. However, let's take a bunch of those single measurements and take the mean. What I'm showing in red is the distribution of the means that result from taking the mean of single measurements. We see that the red distribution is a lot narrower. This is the idea of averaging, reducing variability in action. Averaging lots of measurements reduces variability. So means are less variable than single measurements. Okay, so the idea is for us to build up a lot of very large trees. How do we build up a lot of trees? Here's a naive idea. Let's just build a tree for every training set that we have. Wait a second, we don't have lots of training sets, we only have one. Is there a way for us to get many training data sets from the single one that we have? Yes, otherwise I wouldn't be asking this question. There's a powerful statistical technique called bootstrapping that can do this for us. How does bootstrapping work? Well, in bootstrapping, the idea is to resample our sample with replacement. We want to do a large number, in the thousands, of these resamples. So for example, if our training set, or sample, has 1,000 cases, we'll randomly draw 1,000 cases from our training set with replacement. So if we do B of these resamples, we'll get B different samples. This is why sampling with replacement is absolutely critical. If we did sampling without replacement, we'd get B identical samples because we're drawing the same cases every single time. Awesome. So at the end of bootstrapping, it's as if we now have B different training samples. The goal of bootstrapping is to try to understand and take advantage of sampling variation. You might be wondering where the name bootstrapping comes from. It actually does come from the saying pulling oneself up by one's bootstraps, the saying that we try and pull ourselves up by working very hard, trying to get something from nothing. It's actually a butchering of a tale from an old German set of fairy tales about a fictional character named Baron Munchausen, who pulled himself and his horse out of a swamp with his hair, not his bootstraps. But in any case, in bootstrapping, we try and get a lot out of nothing by working very hard, resampling our sample. So combining bootstrapping with decision trees is called bagging. Bagging stands for bootstrap aggregation or bootstrap aggregating. and bagged trees stands for bootstrap aggregated trees. So the algorithm is this. First, we obtain B bootstrap resamples of our training set. And for each of these B resamples, we'll grow a very large, low bias, high variance tree. And finally, we're going to average or aggregate predictions from all of these trees. So in a regression task, if we're growing regression trees, each of these B trees is going to generate some quantitative prediction. And what we'll do to aggregate predictions from all of these trees is to average them, take the mean. Let's say we're in a classification task, then we're growing classification trees. Well, each of these B trees generates some class prediction, and what we can do to aggregate all of these predictions is to take the majority vote. So let's look at an example for a regression task. What we're looking at here is housing data, and what I've done is bootstrapped my training set 3 times, and I built 3 regression trees in order to predict house price. So the particular test case that I'm concerned with is some house that has a living area of 3,000 square feet. The number of fireplaces is 1, and the land value is $50,000. So what I'll do is make a prediction for this test cases, this house's price, based on each of these trees. So check for yourself that if you follow the branches along, you get the predictions indicated by the arrows. So in the first tree, I predict $331,000 for this house's price. The second tree predicts $261,000, and the third predicts $264,000. To get my bagged prediction of this house's price, I'm going to average these 3 predictions. So I'd predict about $285,000 for this house's price. Let's look at another example, this time for a classification task. So here we're in the heart disease data set. The test case that we're concerned with is shown here. And what I've done, as before, is bootstrap my training set 3 times, and I built 3 trees. Check for yourself that if you were to make a prediction about this patient's heart disease status using this predictor information, you'd get the predictions indicated by the 3 arrows. So in this case, the leftmost tree generates a prediction of no heart disease. Same with the second tree, but the third tree generates a prediction of yes heart disease. So what we can do to combine all of these predictions into a single prediction for this test case is to take the majority vote. In this case, the majority vote is no, so we'll say that no is our bagged prediction of this patient's heart disease status. As is often the case in machine learning settings, we're interested in estimating test error of our models. So a natural first thought is to use cross-validation. How does cross-validation work in this setting? Well, as usual, we'll split our data into k folds. We reserve k-1 folds for training and hold 1 out for testing. So in each of these iterations, we bootstrap the k-1 folds that are reserved for training to generate B bootstrap resamples. And for each of these B bootstrap resamples, we build a large tree. Then, as we discussed in our earlier examples, we generate bagged predictions for each case in the test fold. And then we can compute an accuracy measure from these predictions. So for each of these k iterations of k-fold cross-validation, we have some accuracy, some error measure, and we average these k accuracy or error measures to get an overall estimate of test accuracy or test error. Okay, great. This is how k-fold cross-validation would proceed in the bagged tree setting. But this turns out to be pretty computationally intensive. So just looking at the algorithm, we have to do k iterations of cross-validation. And in each of those iterations, we have to do a lot of bootstrapping. And for each bootstrap resample, we have to fit a very large tree. So all in all, this whole procedure can be pretty computationally intensive. An alternative to cross-validation for estimating test error in the tree setting is called out-of-bag error. Out-of-bag error estimation is also abbreviated with OOB. So the idea is this. When we bootstrap, a bootstrap resample is not going to contain all of the original training cases. So for example, in our first bootstrap resample, it just happens to be that cases 3 and 23 were not sampled. So cases 3 and 23 were not used to build the tree trained on this resample. They can be used as a test data set then. So cases 3 and 23 in this situation are called out-of-bag cases. With enough bootstrap resamples, high enough B, each case will be a test case for some tree. So let's look at an example. Let's say that our training set has 6 cases and we bootstrap 5 times to generate 5 trees. So the 5 trees are shown here. The bootstrap resamples are also shown, and I've also highlighted which of the 6 training cases are not used in constructing each of these 5 trees. So let's look at case number 1. Case 1 is used in training trees 1, 3, and 5. Case 1 happens to be out of bag for trees 2 and 4, so it can be used as a test case for those trees. So what we do in out-of-bag error estimation is we use trees 2 and 4 to make predictions for case 1, and then we combine these 2 predictions in order to get a single prediction, as we discussed before. So in a regression setting, we average these 2 predictions, and in a classification setting, we take the majority vote for these 2 predictions. So we have the true response for case 1. We have the single prediction now for case 1. So now we can compute accuracy or error. And that, in a nutshell, is out-of-bag error estimation. So pause the video here and check for yourself how things work out for cases 2 to 6. For which trees are cases 2 to 6 out of bag? Okay, so the answers are shown here. For each one of these cases, we can see for which trees is it out of bag. So for example, case 2 is out of bag for tree 4. It can be used as a test case for tree 4. So for all of these cases, we combine predictions from the trees for which it's out of bag to get a single prediction for each case. Because we have the true response for each of these cases, and now we have all of these predictions, we can compute overall accuracy or overall error. Okay, so now we've talked about bagging, and it's natural to ask, can we actually improve upon bagging? And we can. So let's notice a few things from the trees that we looked at in our earlier examples. So the first part at the top shows the tops of the trees, the tops of the 3 bootstrapped or bagged trees for the housing data set. So notice that living area is always the top split, and land value is always a subsequent split. So all of these trees actually look pretty similar. Okay, and in looking at the heart disease data set at the bottom, notice that almost all of the trees start with chest pain or the CA variable. They're all pretty similar trees. So this idea that in bagging, all the trees can be pretty similar when you have a particularly dominant predictor is an important one that we can improve upon. So idea number 2 is to encourage more diversity in the trees. So the statistical idea is this. Averaging predictions does reduce the variance of a final prediction, but averaging highly related predictions doesn't reduce this variance a ton. So in bagging, the trees tend to look pretty similar. So in other words, they generate pretty related predictions. Let's decorrelate the trees. Tree decorrelation is the key idea behind the random forest algorithm. In random forests, we try to decorrelate the trees by forcing every tree to use a different subset of the predictors. So the algorithm is actually the same as bagging, but with one small tweak. In bagging, when we build a single decision tree, every split is allowed to consider all of the possible predictors. We tweak that in random forests. In random forests, every split in building a single decision tree is only allowed to consider a random subset of M predictors. Usually we pick M to be about the square root of P, where P is the total number of predictors. So in practice, we very frequently combine bagging with tree decorrelation by using random forests. This ends up working particularly well when P is huge and a lot of the predictors are correlated with each other. So in summary, decision trees aren't that great by themselves, but we've seen in this video two ideas that can make them a lot better. The first idea is to use a lot of trees. This is the bagging or bootstrap aggregating idea. It's the idea that if we take a lot of predictions and average them together, we get a more stable prediction. The idea that averages tend to be less variable than the individual measurements. Well, we did notice a problem with bagged trees. It was that a lot of the trees tend to look pretty similar. This can happen often if you have a particularly strong predictor. It'll always show up as the first split, and this will make all of the trees look pretty similar. So idea number 2 is to diversify the set of trees. Random forests do this. Random forests decorrelate the trees by forcing each tree to use a different subset of predictors, a random subset of the predictors. Finally, we have covered the idea of out-of-bag error estimation. It's a faster alternative to cross-validation for estimating test error, especially in these tree settings, in these bagging/random forest settings.